Hello there, Mr. Sutton bringing you the AB Calculus Chapter 5 Quiz Theory Review Solutions on Fundamental Theorem. For this problem, we're given this integral function with x in the upper limit of integration, and we're trying to find the derivative of this thing. With x in the upper limit of integration, whatever variable is up there, we're just going to substitute that in for all of these variables inside here, all the dummy variables. And if there was a tail, we would multiply by that, but the derivative of x is just 1, so the chain rule doesn't really apply a whole lot here. So we're just going to end up then with x cubed plus 7x squared plus 15x plus 12, and that's it. For this problem, I'm trying to find the derivative of this integral function. Since I've got 2x in my upper limit of integration, I'm just going to substitute this variable expression, 2x, in for the dummy variable here. So I'm going to have 2 over 2x plus 1 squared. But since I'm taking a derivative, I have to use the chain rule and multiply by the derivative of 2x, which is 2. So then I've got 2 over 2x plus 1 squared times 2, which if I wanted to, I could simplify to 4 over 2x plus 1 squared. For this problem, I'm trying to take the derivative of this integral function that has an x cubed as its upper limit of integration. So since I have a variable up here, I'm just going to replace the dummy variable t with x cubed. So I'm going to have 4 parentheses x cubed plus 3 to the 1/2. But since the tail of x cubed is not just 1, I'm going to actually have to take the derivative of x cubed, which is 3x squared, and multiply by that as well. So that's the chain rule being applied here. And if I want to simplify this, I could multiply it out to get 12x squared times x cubed plus 3 to the 1/2, or the square root of x cubed plus 3, either way. Now note that this lower limit of integration, it doesn't really matter what constant this is, and you could see that if you actually took the integral evaluation of this stuff and then took the derivative, this -3 would just give you a bunch of constants that got zeroed out. On this problem, we're given the graph of differentiable function f, and then we have this h function that's essentially the integral from 0 to x of that f function. We want to order h of 2, h prime of 2, and h double prime of 2. So the name of the game here is figuring out the connection between f and h. Because we have a graph of f, but they're asking us a whole bunch of stuff about h. So the connection, you can see it if you take the derivative of this equation they gave you. H prime, you will see, is actually just f of x, if we use that first fundamental theorem of calculus. And that'll help us on at least some of these. Now let's start with h of 2. H of 2 is just going to be the area under the f function between 0 and 2. So if we look from 0 to 2, we don't know how much this area is because they didn't really label any y values or anything, but it is below the x-axis and we're moving to the right. So that means this is a negative area. So hopefully that helps us order these when all is said and done. Now since h prime and f are really the same thing, that means h prime of 2 is really just f of 2. And f of 2, assuming these grid lines are going by 1s, which we have to assume if they're not labeled, f of 2 is just 0. It's right on the x-axis. Finally, h double prime of 2, that is basically f prime, the slope of f, at 2. Well, at 2, we're going up, we're increasing, so that means that f prime is positive there. So if I have a negative, a 0, and a positive, the negative is going to be the smallest out of those. The 0 is going to be next, so h prime of 2 is next. And then finally, h double prime, the positive, is going to be the biggest, and it's going to come last. For this problem part, we want to know, based off of this g function here, for what values of x the graph of g has a point of inflection. Well, if I want to know where g has a point of inflection, it would be helpful to know either where g double prime is changing signs, or if I can't really figure too much out about g double prime, at least where g prime is reversing directions. So let's start with g prime, either way. G prime, using our fundamental theorem here, that's just going to be whatever you get when you plug this upper limit of integration into this dummy variable. So this is just going to be g prime of x equals f of x. That's a good thing to establish right off the bat. And I notice on my graph that g prime, also known as f of x, is reversing direction, changing from decreasing to increasing at about x equals 1. And it's also changing from increasing to decreasing at x equals 4. So we have two direction reversals. This is telling us that g has points of inflection at both x equals 1 and x equals 4. On this problem, we're trying to find the definite integral from 0 to 4 of 2x plus 1. So for this one, we're just going to use our integral evaluation theorem, basically the second fundamental theorem of calculus, take the antiderivative of this, and plug 0 and 4 into it. So first step, antiderivative, 2x, that's going to become x squared if we bump that up to a 2 and divide by 2. And then 1 becomes x, and we're evaluating that from 0 to 4. So I'm basically doing 4 plugged into all this stuff minus 0 plugged into all that stuff. That's going to be, let's see, 20 minus 0, which all just comes out to 20. On this problem, I'm trying to take the integral from 1 to 2 of this polynomial. So I'm just going to go ahead and use my integral evaluation theorem. So antiderivative of this stuff, this becomes x to the 4th. Dividing by 4, we just have a 1 for the coefficient. So just x to the 4th then, minus, this bumps up to a 3. Dividing by that, we've got minus 1/3 x to the 3rd. And then this will be minus 2x, all evaluated from 1 to 2. So we have 2 plugged into all this stuff, minus all this stuff with a 1 plugged in. And if it's a free response, you could leave it like this. If it's a multiple choice, you'll need to simplify it. We'll simplify it just for the sake of argument here. So over here, I'm going to take a few steps to simplify this with all the fractions. So this is 16 minus 8/3 minus 4. And over here, I've got 1 minus 1/3 minus 2, but all that gets negated. So I have negative 1 plus 1/3 plus 2. Collecting like terms, I've got, let's see, 16 minus 4 minus 1 plus 2. So all those non-fractions, that's going to be 13. And then we have a minus 7/3. This is really 39/3 minus 7/3. So we could simplify that to 32/3. For this problem, I'm trying to take the definite integral from 1 to 4 of 5 over x dx. Antiderivative of 5 over x, that's going to be 5 times the ln of absolute value of x, evaluating from 1 to 4. So that's this stuff with 4 plugged in minus this stuff with 1 plugged in. 5 ln of 4, can't really do too much there, but ln of 1 is 0, so this whole second term is just gone, and 5 ln of 4 would be the simplified version of this. For this one, we want the integral from 1 to 3 of 8 over x cubed. There's actually a vertical asymptote at x equals 0, but that's not going to affect us since we're going from 1 to 3 here, so we won't worry about it. I'm going to rewrite this as 8x to the negative 3rd. Using my reverse power rule, this bumps up to a negative 2. Dividing by that, we have negative 4x to the negative 2, going from 1 to 3. So plugging all that in, we've got negative 4 over 3 squared, and then we're going to have essentially plus 4 over 1 squared, because we're going to have a minus minus for that second piece where you plug in 1. So this is negative 4/9 plus, I guess you could call this 36/9, so 32/9 if you wanted to simplify it. For this one, I want the integral of negative 4 sine of x dx from pi over 3 to 2 pi. Let's take our antiderivative first. So that's going to end up being 4 cosine of x. And now we're going to integrate that from pi over 3 to 2 pi, or rather plug it in here. So I've got 4 cosine of 2 pi minus 4 cosine of pi over 3. And I'm going to actually pull the 4 out and just do that cosine stuff inside of parentheses, just because. So I've got cosine of 2 pi inside minus cosine of pi over 3. Cosine of 2 pi, or cosine of 0, that's just 1. And then cosine of pi over 3, well, that's going to be 1/2, so minus 1/2. So I've essentially got 4 times 1/2, which is just 2. I want now for this one the integral from 0 to 7 of 4e to the x. Well, the antiderivatives on this one's pretty easy. It's also 4e to the x. Plugging in 7 and 0, I've got 4e to the 7 minus 4e to the 0. 4e to the 7 is what it is, but e to the 0 is 1, so this is really minus 4 then, if you needed to simplify it a little bit more. For this one, I'm trying to find the integral from 0 to 2 of this piecewise function. Now this one, they gave us a border value of 1, and our integral kind of spreads over that, so we're actually going to need two different integrals in order to do this one. We need the integral from 0 to 1 of this first rule, x to the 5th minus 1, plus the integral from 1 to 2 of this second rule, negative 2x plus 1. All right, well, let's do our first antiderivative. That's going to be, let's see, this bumps up to a 6, so 1/6 x to the 6th minus x. And again, that's going from 0 to 1. Over here, this becomes negative x squared plus x from 1 to 2. So we'll do this one first. That's going to be this stuff with 1 plugged in minus this stuff with 0 plugged in, plus this stuff with 2 plugged in minus this stuff with 1 plugged in. Whole bunch of evaluating to do. So I'm going to do one bracket at a time here. If I actually have to simplify this, if it's a free response, I would just leave it like this and be done with it. But over here, this is going to be 1/6 minus 1. That's negative 5/6. Here, this is just a bunch of zeros, so I'll just write 0 to show that I actually did look at it. Over here, this is negative 4, because the exponent happens before the negative. So negative 4 plus 2, which is negative 2. And over here, we've got negative 1 plus 1. That's also 0. So then we just have essentially negative 5 over 6 minus, you could call this 12 over 6. So that's negative 17 over 6 when the dust settles. For the next several problem parts, we're going to use this graph of f and also the g function, which is the integral of the f function from 0 to x. So we want to find three different things for this part here. Let's start with g of negative 1. That's the integral from 0 to negative 1 of the f function. That's the area under f from 0 to negative 1. Now the tricky part about this is we're going backwards. We're starting at 0 and moving left to negative 1. So this area, this triangle area here that we're going to be counting, normally that would be positive because it's above the x-axis. But since we're going from right to left, everything becomes opposite of what it would normally be. So this is actually going to be a negative area, negative 1/2 times a base of 1 times a height of 3. You don't have to simplify it, but if you do, that's negative 3/2. Moving on now to g prime of negative 1. Well, g prime of x is really f of x if you take the derivative of this integral with x in the upper limit. So that means that g prime of negative 1 is really f of negative 1, which is just the value of the f function at negative 1. Right here, that's going to be y equals 0. And then finally, g double prime of negative 1, that's just f prime of negative 1. That's the slope of the f graph at negative 1. So we look here, we are on a straight line here, so that's a constant slope. So if we find the slope of this whole line, then we've answered the question. You actually could read the slope off the graph. I mean, you're just going up 3 and over 1. That's clearly a slope of 3. But if you wanted to show the slope formula, you have 3 minus negative 3 over 0 minus negative 2. So 6 over 2 again comes out to 3. And there you go. For this part, we want to know for what values of x in the interval from negative 2 to 2 is g increasing. Well, to know where g is increasing, we need to know about g prime and what that's doing. So we saw before that g prime is really just f, using our fundamental theorem to make that conversion. So I just need to know then what the sign of f is doing, because if I know the sign of g prime or f, they're the same thing, then I know where g is increasing or decreasing. Since g prime is positive from negative 1 to 1, since it's greater than 0 on negative 1 to 1, we can conclude just using this that g is increasing on the interval from negative 1 to 1. For this next part, we want to know for what values between negative 2 and 2 is g concave down. So for this, we need to talk about the direction that g prime is going. Again, remember that g prime is really just the f function. And for concavity, we're talking about whether g prime is increasing or decreasing. since g prime is decreasing, going down from 0 to 2, that means that therefore g is concave down on that same interval. For this one, we're trying to find the max value of g on the interval from -2 to 2 and justify our answer. So that means we need to either use the candidates test or the lonely critical value test. Now we've got multiple critical values here. We've got critical values at -1 and 1. So we actually can't use that particular test. We need candidates test on this one. So we're going to have to test out -2 and 2 in the g function and whatever critical values meet certain criteria between those. So remember again that g prime is really just f, and this changes, since we're looking for maximum, the absolute max here, we only actually need to consider local maxes. G prime changes from positive to negative only at x equals 1. So therefore, we actually don't need to test out x equals -1 during our candidates test. You still can if you want, but once you've made this statement right here, you're free to just test this one critical value that's a local max. All right, so let's test them all out. G of -2, so that's going to be going from 0 to -2, and that's going to involve subtracting this triangle like we did before. Actually, I feel like we did this before. Now, that was g of -1 that we found. So this is g of -1 right here, subtracting that triangle. But we also have this other triangle now to take into account. Since this is below the x-axis, but we're going from right to left, this is actually going to be positive area down here. So this is going to be plus 1/2 times a base of 1 times a height of 3. These two things are exactly the same except for the sign, so that just cancels out to give us 0. All right, well, let's take a look at the next one. We have to test out g of 1. That's just going to be positive area above the x-axis here. So that's going to be 1/2 times a base of 1 and a height of 3. You're going to see that all of these triangles involved in this problem actually have the exact same area of 3/2. And then finally, we have to test the other endpoint, g of 2. That's going to be this first triangle area plus this negative triangle. It's below the x-axis, and we're going left to right. So that's a -3/2. So that also is going to be 0. And then looking at all our values here, our max value is going to be this 3/2 because it's bigger than the others. For this last problem part, they're introducing a new function, h, and we're trying to find h of 2. Now what they've given us to go on here is that h prime is really just f of x, so this graph here, and h of -2 is 10. Given this, we're going to have to use our fundamental theorem to get to the bottom of this. So we can say that h of 2 is going to be h of -2 plus the integral from -2 to 2 of h prime, which is to say the integral from -2 to 2 of f of x. So let's plug in our values here. We've got 10 for h of -2. They gave us that. And now we're finding the area going from left to right of this whole graph now. Now, you got to be careful because you're used to starting at 0 and then going left or right. But the way this is written, we're going from -2 to 2. We're starting at -2 and just subtracting or adding area normally as we go. So the first area we see is this negative triangle here, which we've already seen many times is an area of 3/2, but it's under the x-axis and we're moving right. So that's -3/2. Next, we've got this triangle up here. We have 1/2 times a base of 2 times a height of 3. So that's going to end up being 3 when all is said and done. And then we have this other negative triangle, which has the same area as the first negative triangle. All right, well, adding it all together, we've got +3. These two negatives become a -3, so all of this actually ends up canceling out, and you just end up with 10 when all is said and done.